Is Forrey, which is going to talk about something really relevant for a lot of people in this building, about chemical reaction for astrophysics, for 2 and 3 body process. So please, the floor is yours.
Thank you. So first, I would like to thank Harvard University for the generous support of this workshop, particularly in light of the comments that Hossein had made earlier, challenges and so forth. And I'd also like to thank the organizers for inviting me to speak here today. So as you can see, I will be talking about molecule formation in astrophysics via 2 and 3 body processes. The work that I've done in this area has been supported by the National Science Foundation. And in light of the astrophysical context, I thought I would start with a really interesting paper that appeared in 2011 by Chark and co-workers, where they described gravitational collapse simulations of the first stars in the universe, the so-called population 3 stars from primordial gas. And what they found in their simulations was that these macroscopic simulations were very sensitive to a single microscopic parameter, the so-called 3-body recombination rate, which is K sub r here in this picture. So they used available rate constants that were in the literature. And for the smallest ones that they found, the outcome of their gravitational collapse simulation was that there would be a spherical collapse that you see up here. It would take a long time, very inefficient process. And then it would it would end up as a very high mass, extremely high mass first star. For other values of the 3-body recombination rate, moving down, they found that there's some sort of spiral structure in the collapse, non-spherical collapse. And this tended to fragment the collapse process into multiple smaller mass first stars. So very different outcome depending on the published values of the 3-body recombination rate. So it's very unusual for a macroscopic simulation to be this sensitive to a single microscopic parameter. So that's a sign, I think, or a challenge, so to speak, to our community to try to pin that number down better than it had been. And so that's what I want to talk about first. Maybe just to give a little more context, a simple cartoon of the gravitational collapse process. We all know gravity is very weak, and in fact, in AMO physics, we generally ignore it. But in astrophysics, it's relentless. It's constantly trying to contract a gas of particles. And if the particles don't have any internal structure, the process just stops because the particles fight back by heating up and the system just reaches an equilibrium and nothing interesting happens. But of course, the particles have internal structure. The particles are atoms and molecules. And so the high-speed particles that are being compressed bump into each other. And what happens is the atom or the molecule, shown here as a sphere with internal energy, simply gets excited. That slows the translational energy of the colliding particles. And then when the system relaxes, the internal energy radiates away, leaves the cloud, and then the process of gravitational collapse can continue. And this can continue on and on, presumably until nuclear core fusion burning takes place to make it a star. Molecules are particularly important because, of course, the internal energy structure for molecules are much closer spaced. So molecules become the primary coolant. And so the 3-body recombination of atoms into molecules is really the critical question that I wanted to study. So how do molecules form? Well, it's well known. It's been studied for a long time. You have 2 atoms, A and B. They're far apart. They come together, and then they can form a molecule either through a non-resonant pathway, which would mean if there's a potential energy barrier, they would just go above the barrier, or they could form a resonant pathway where they would tunnel through the barrier. But in either case, they reach the interaction region where they can stabilize and form a molecule either by emitting a particle, say a photon, if it's a radiative association process, or by colliding with a third body, which is the process of 3-body recombination. So let's look at the 3-body recombination as it's currently understood. So the direct non-resonant process would be the 3 atoms just come together. M is the colliding third body, and then the H's form a molecule. Another two-body indirect pathway, there's two of them that are generally referred to as the energy transfer mechanism or pathway, or the exchange or chaperone mechanism or pathway. There you see these three dots. Those three dots represent a resonance typically, although I'll come back to that point. But if those three dots represent a resonance, then this indirect process can form a molecule. And then typically what people will do is just add the three pathways together that you see here. And this then would become the three-body recombination rate. Now you have to be a little careful here. If the three dots don't just mean resonances, but in fact, if those three dots represent the entire interacting two-body continuum, then it was shown back in 1996 by Snyder and coworkers that, in fact, these different pathways should give you the same three-body recombination rate. Now, this pathway independence was shown formally in their paper using operator theory. But later on, I used this as the foundation for the Sturmian theory that I developed and will want to talk about. In fact, could independently, using the Sturmian representation formalism, show that that this is a complete description of the three-body recombination process. Question?
Sorry, when you speak about the entire interacting continuum, included, of course, for a quasi-bound state.
Yes, it includes quasi-bound states, and I'll show you exactly what it includes for the hydrogen problem. But yes, it includes it includes non-resonant as well as resonant interactions, and so everything is got to be included. And if you do that, and the assumption here also is that you have an isolated system, and so that's key to both their demonstration using operator theory as well as the Sturmian representation. You have an isolated system, and I'll talk about dissipative systems as well. All right. So there's an additional sort of a controversy that even within a given pathway, is it the resonances or is it the non-resonant background that is dominating the process? So the literature is filled with conflicting reports, which is great, right? It means you can keep studying it. So the classic paper that started it all, as far as I understand it, was in 1969, Roberts, Bernstein, and Curtis. This is sometimes called the RBC paper. It's also the beginning of what is known as orbiting resonance theory. And so in their paper, they argued that orbiting resonances are the dominant recombination mechanism. And then this sort of started a whole bunch of additional follow-up papers by many groups using the orbiting resonance theory. And they all echoed the idea that orbiting resonances are very important, although they eventually started to, this is just one example, the Bain-Bartley, a famous paper, that it's important to make sure that the resonances aren't too long-lived. So then it became a question of choosing the resonances which are important and discarding the ones that are supposed to get discarded. And this became a little bit of an art as much as the science in terms of the kinetic part of the problem. So some years later, there were some really important papers by David Schwenke and the Los Alamos group that did a master equation study. And these are very rigorous calculations. And what they found was that, in fact, it's not the orbiting resonances that are a dominant mechanism, but in fact, it's the non-resonant three-body collisions that are dominating the recombination. And so naturally, I didn't really know what was going on, so I wanted to find out. So what is really going on? And the first thing I want to talk about is a very old picture of the indirect energy transfer pathway within the orbiting resonance theory. And so in this picture, there's two steps, as I mentioned earlier. You have an activation step, and this is typically a two-body activation step. And then this is followed by a three-body stabilization step. And in this picture, here the star indicates a quasi-bound resonance. The brackets that you see here just represent concentration. So that represents the concentration of the resonant AB molecule. And it's very easy within the steady state approximation to get the form that you see here. And then you put that into the definition of the three-body recombination rate, and just substituting the concentration here and here, and you get the very well-known three-body recombination rate that you see in chemistry kinetic textbooks. And what you find is that you have a concentration of the third body, C, in the denominator. And what that does is when C is small, then the recombination rate doesn't depend really on the third body concentration, and you just get third order kinetics. That just means that the rate constant, which is constant, multiplies 3 different concentrations. Right? But when that concentration of the third collider C is large, then this C here in the denominator dominates over the other part. And then that C is going to cancel with the C here in the definition, and you get second order kinetics. And so because there is generally an isothermal process, that's the same thing as a pressure dependence. And this is often referred to as pressure fall off in the 3-body recombination community or in the collision-induced dissociation community. You get this pressure fall off. And it's due to the depletion of these quasi-bound states that you get when the third body is very highly concentrated. Now, in polyatomic systems, I don't know how many people work on polyatomics, but in polyatomic systems, it's well known that fall off does actually occur. It's observed. Pressure fall off is very routinely observed. But for atomic recombination, it's not. There is no real evidence that I'm aware of, no experimental evidence that there is any pressure fall off for atomic recombination. And the reason is that the 3-body collisions keep the quasi-bound states from being depleted. This was something that the Los Alamos group pointed out, and I think it's correct. And for atomic systems, this is always going to be the case. For polyatomics, there's 2-body activation that does not require tunneling that can dominate over the 3-body collision. So that's why the situation changes a bit. But for atomic systems, this is an important understanding. And I think it's important for people to realize that this pressure fall off, it's not relevant for atomic recombination. So let me look at that. What I just showed was a phenomenological picture where all those rates were sort of like a net rate effect. But I want to look at a microscopic picture, which has all the state-to-state information. And for hydrogen, we'll start with the well-known resonances that occur for hydrogen. There's about 60 of them, as you see here. And the stars, there were 6 starred resonances. Those were the ones that were used by the original Roberts, Bernstein, and Curtis. And then there are many other what are often called above barrier resonances that have an observable time delay. And then you see some really narrow ones. I put boxes around the really narrow ones. Some of these resonances have lifetimes that are comparable to the age of the universe. And then in addition, you have the entire non-resonant background. And so what I've chosen to do is use the Sturmian approach, which allows you to treat all of these unbound states together as a quadrature representation of the 2-body interacting continuum. And so that's what I want to talk about next. So in the Sturmian approach to 3-body recombination, you start with a phenomenological rate equation that's common to any method. But then you write down a master equation, and the rate equation needs to be consistent with the microscopic rate equations, the set of rate equations, or the master equation. And typically what people who study master equations do is they'll diagonalize a rate matrix and then maybe interpret the slowest eigenrates as these coefficients in the rate equation. In the Sturmian theory, you don't need to do that. You can actually write down a closed form expression that you see here. So the solution of the master equation are the concentrations. These coefficients are bimolecular rate constants or rate coefficients. And you can just sum over unbound and bound states. The nice thing about the Sturmians is they're unit normalized, as are the bound states. And the sum over unit normalized Sturmian functions is equivalent to an integral over an energy continuum. The usual energy normalization exactly compensates for the quadrature weights in the Sturmian representation. So these are complete closed form solutions for the recombination and collision-induced dissociation rates. And for a isolated system, you can show, and you must return the Boltzmann factors that you would expect from an equilibrium system. And this is a very transparent way of arriving at the well-known statistical Saha equation, which characterizes the conditions of local thermodynamic equilibrium. So let's look now at the energy transfer pathway in the Sturmian representation, which includes all of the state-to-state possibilities. We have the closed form solution. You can write it as a non-resonant and resonant piece, like I showed earlier. And then when you solve the master equation to get the steady state population of all of the unbound states, this is the same thing that you see here. this is a general result which applies for both the non-resident and the resident contributions, because the tunneling lifetime, if you have a barrier, would be non-zero. But if you had no barrier, you can just set the tunneling lifetime to 0, and you get back the equilibrium constant. And so it also works for the non-resident piece as well. So it's a very general formula. And I should mention here that if we try to connect back to the orbiting resonance theory, what you see is there's 2 approximations that the orbiting resonance theory is actually making. The first is they're just ignoring the non-resonant part altogether, right? And that's very clear, I think, because the orbiting resonance theory assumes you're dealing with resonances. But they're doing something in addition to that. They are getting rid of this kinetic feedback term, and that kinetic feedback term can be very, very important. And once you get rid of that kinetic feedback, this equilibrium constant, which is generally due to the 2-body activation, divides now a long tunneling lifetime, which then multiplies by a large concentration due to this pressure dependence. And then this is responsible for this idea of a fall off. But it doesn't exist for atomic systems. And the reason is the kinetic feedback needs to be included. So I just want to emphasize that both of the neglected contributions in the orbiting resonance theory involve 3-body collisions, and they should be included. So let's do it. If you put everything in, you include the non-resident, that's not too bad. But now the kinetic feedback looks a little messy. But for an isolated system, this is an exactly solvable problem. It's not hard using detailed balance arguments and some matrix linear algebra. It's not hard to show that the 3-body term here in the numerator is going to have the same dependence as the 3-body term in the denominator. And in fact, it exactly compensates for it, so that the 3-body term is going to give you the same equilibrium constant that you get for the 2-body activation. And this is to be expected for an isolated system. But it's nice that it's easy to show it, and it's certainly valid. And then the question becomes, what about a dissipative system where maybe you don't know what the steady state solution is going to be? Well, in this case, you can also show that whenever 3-body recombination is important, meaning whenever you have this term in the denominator that's large, well, then you're going to get this term in the numerator at the same scale. And you're going to end up with the same idea here, that the 3-body equilibrium constant is going to return the same thing as the 2-body equilibrium constant that you would get just if you didn't worry about the 3-body terms. Anyway, the take-home message here, again, atomic 3-body recombination rate does not depend on pressure. All right, so I want to look at some results. Okay, so here's some classical trajectory results for hydrogen. These are the best classical trajectory calculations that I know of for hydrogen. And so it was done by Esposito and Capitelli back in 2009. And so they did classical trajectories for all of the direct collisions, and then they added the resonant contributions using orbiting resonance theory, and they got the pressure dependence that you see here. These are 2 different surfaces. The BKMP2 is the more recent 3-body surface. Originally, there was an LSTH surface. But what they found was basically the same trend, and that is that there was, comparable 3-body recombination with high pressure results down below and low pressure results up high. And I, of course, am arguing that, in fact, self-kinetic or self-consistent kinetic theory, there should not be such pressure dependence. And the argument, again, is because the 3-body collisions are maintaining the population of the quasi-bound states. So I get a single curve, here it is, the red one, using a quantum calculation, which I'll talk about a bit. And it falls in between the high pressure and low pressure classical trajectory results of Esposito and Capitelli. And it's within about a factor of 2 of the high and the low pressure results, which is encouraging, especially because I'll talk about in a bit that the quantum calculations that I did, which used an energy sudden approximation, which is generally regarded as a pretty severe approximation. But remember, we're at high temperatures, right? These temperatures here where the star formation needs better data, these are very high temperatures. So the energy sudden approximation is not as bad of an approximation as you might think. I'll talk about that in just a bit. And I found that there's good reasons by comparing to a couple of states calculations and so forth, at these temperatures, there's very good reasons to suggest that the energy sudden proximity is reliable. And so I claimed a factor of 2 accuracy for my calculations, which then got used by the astrophysical community. Bovino and coworkers sort of redid these gravitational collapse simulations, and they used my so-called new accurate 3-body formation rate, which is a little generous because I was only suggesting that they were good to a factor of 2. All right. Anyway, that was sufficient, however, to undo or to remove the uncertainty that had existed in the previous gravitational collapse simulations. All 3 of these dark matter halos that they studied collapsed to followed a spherical collapse pattern to a high mass first star. And so I think that was kind of a success. I don't know that it's the last word because, of course, with Webb telescope, we're finding out all the time that what we think we understand, maybe we don't. So we should maybe keep an eye on this. But I think it helped to remove some of that original uncertainty. All right, let me turn now to a dissipative system, which the steady state solution is not expected to go to the LTE result. And therefore, there will be a pressure dependence because there's competing processes. At low density of gas, you have 2-body radiative processes will dominate. But then at high pressures and high concentrations, you'll get back to 3-body recombination. And so there's going to be some transition between the low and the high density. So you are going to expect now to see some pressure dependence. And here you can again use the Sturmian formulation. You get the ratio of the recombination and the dissociation. The only difference here is that your steady state solution now has a coefficient here in front of the Boltzmann factors. And this coefficient is something I refer to as a non-LTE coefficient. It can be calculated from the master equation, but when it goes to 1, it has to when the pressure is high, meaning the concentration is large, or equivalently, if the blackbody radiation temperature is the same as the matter temperature. Both of those conditions will cause this to go to 1 and give you back the Saha equation. So solving the master equation is sometimes not practical and sometimes not even feasible, depending on what information you have available for the different processes that go into it. So it's nice to actually look at some limiting cases to see if you can gain some understanding. And so the first limiting case is what we refer to as a non-LTE zero density limit. And so this limit is exactly what you would think based on the name. There's no 3-body collisions at all because it's so dilute, and there's no radiation field. So you have no mechanisms for dissociation, no mechanisms for three-body recombination. The only thing that can happen is radiative association. And then in the opposite limit of high pressure, now you have LTE. And so you have an LTE radiative association, which is different than the non-LTE radiative association, even though those are two-body terms. They're not the same. And then you have the 3-body case that I just talked about. So questions that arise are, what is the difference between the LTE and the non-LTE 2-body rate? And then once we achieve the LTE, maybe the 2-body, which is easier to calculate, could be used to estimate the 3-body rates in that limit. So those are 2 questions that I wanted to look into. Here's some calculations for silicon colliding with oxygen to form SiO. And first, we looked at some semi-classical calculations. These were done by Jim Babb, who's here today. And what you see is the semi-classical results agree really well with the zero density limit quantum results shown in red. The only difference is that the zero density quantum results have some very broad resonances that the semi-classical can't pick up, and that becomes more important at the lower temperatures. But more importantly, the LTE versus the non-LTE 2-body rates are very different. And in fact, the trend is exactly the opposite of what the orbiting resonance theory, as it's currently used by most people, would lead you to believe, right? So the blue curve is high pressure, the red curve is low pressure. And so this makes a big difference in terms of the 2-body rates, and it's all coming from how you're handling the 3-body kinetic feedback. So let me try to show some results which can maybe explain why there is such a big difference. So here you see the cross section for the radiative association. And in the blue, you see there's a whole bunch of narrow resonances that are contributing on top of the non-resonant background. And they need to be added together. And the Sturmian approach is very simple. You just add them up and you would get a big result. But in the zero density limit, which is the red curve here, you see you have some resonances, but they're not as sharp or they're not as high in their scaling. There's not as many because some of the really narrow ones get filtered out. And here, the reason they get filtered out is because in the zero density limit, the kinetic feedback is gone. There is no possibility of any three-body collisions to provide the feedback. And so you have no three-body collisions in the denominator here. All you have is the radiative decay. And in fact, this formula, which is a solution of the master equation, is exactly the usual radiative broadening formula that people have been using for a long time. So that limit is a good limit. And then, of course, as the density gets greater and greater and greater, the kinetic feedback will start to become more and more important. But at the zero density limit, it's gone. And that's why you get a big difference between the LTE and the non-LTE limits. Another thing that Jim and I did that I think is kind of interesting is shown over here on the right. So Jim calculated using perturbation theory on an energy grid, what we call a grid-based method, energy grid using perturbation theory, calculated the cross sections, and we compared them with the Sturmian method. The Sturmian method is shown in red, and in black were Jim results on the grid-based method. And so what you see is that if the energy grid is too coarse, what happens is you miss some of the resonances, and some of those resonances are important, and you need them. On the other hand, when Jim tried to use a really fine energy grid, what he found were some of these really sharp, high, non-physical peaks that are much higher than they should be, and they're unphysically high. And so this is known in the literature as a breakdown in perturbation theory, but it's not known by everybody. It's still confusing to people. Even today, even though there's been enough written about it, even today, people don't always get it right. So I'll just give you a quick aside that pertained to results that I had calculated. So back in 2016, I was interested in the possibility of quadrupole radiative association in the early universe. I wrote a paper on the topic. And then in 2019, Perez et al., this is not Jesus, not Jesus. They came and said that my rates were too small by 7 orders of magnitude. So normally, I worry about factors of 2, right? Like I showed earlier.
10 million among friends.
Right. So at any rate, when I saw in the prestigious astrophysical journal that I was off by 10 million, well, I knew that I was moving up in the world. I also knew that these guys were wrong because what they failed to appreciate was that the Sturmian method correctly scales these very sharp resonances. Furthermore, a big part of their criticism was that I did not energy normalize the Sturmians, and they're unit normalized, as I said. If you do the thermal average, the quadrature weights, as I said earlier, exactly cancel with the energy normalization, so you don't need to do that. They said that my rates needed to be energy normalized, but they didn't compute the thermal average because it's hard to numerically integrate such sharp structure. But if they did, and I've done it, it's very hard and it's clumsy, and trying to numerically integrate all of those really sharp structures in blue that I showed earlier, if they did that, they would find that this 7 order of magnitude would go away. Now, they didn't do it. I didn't do it either. I just believe it would go away. At any rate, I stand by my calculations. I think they're correct. And I think it's due to the scaling of these narrow resonances that's at the issue. And there were other examples in the literature of misunderstanding of this important point. All right, so let me move back to the question of whether you can use 2-body rates to estimate 3-body rates. So here we're looking at the 2-body zero density limit, radiative association, and then you see the asymptote for the LTE. And then you see here the 3-body multiplied by the concentration in order to get the units to be the same. Down here, it may not be linear. There's probably curvature down here, but it doesn't really matter because it's so small that nobody cares, right? But I just draw it as a line. So that linear behavior will cross at some point with the 2-body. And at this stage, that determines the critical density where the 2- and 3-body rates are the same. And if you know where that density is, then you can use, as I'll show, the 2-body rates to estimate the 3-body rates. Before I do that, let me just make contact with the polyatomic case because it is important because in polyatomic 3-body recombination, there is the pressure fall off, right? You see this. And the reason that this is observed is because in the case of atomic recombination, the two-body step, it can only occur through tunneling. But in polyatomic systems that have internal structure, you can have two-body activation that occurs without tunneling, and that can dominate any kinetic feedback that you would have in the numerator that I showed earlier, and therefore you can get the fall off that is observed using the conventional orbiting resonance theory approach. So, so I just want to make sure that no one thinks that I'm saying pressure dependence is generally not part of three-body recombination. It's just for atomic states that have no internal structure. All right, so let's look at estimating three-body recombination from two-body processes. The black curve are the quadrupole rate of association rates that I just mentioned, scaled by what is a known accepted value for low-lying row vibrational levels of hydrogen, about 10 to the 4. And the red and the blue are three-body recombinations as helium and hydrogen third bodies. And what you see is that the two-body rates fall in between the three-body and basically get the shape the same. So this would suggest that maybe you can do this, but you need to be careful with this assumption because the three-body rates that were done here use this energy sudden approximation that I told you about earlier. And as the temperature goes lower, that has to break down, and it does. And so the fact that this behavior over here for smaller temperatures is in good agreement needs to be carefully considered. So to make this point a little more clear, I did some coupled states approximations, and coupled states are not perfect, but they're a lot better than energy sudden. IOS is another name for the energy sudden approximation. And so what you see is that these are two experiments that exist. In the blue curve, which is the coupled states, captures the trend of the experiment. And coupled states calculations, historically, when compared to more accurate coupled channel calculations, are oftentimes within a factor of 2, but generally give you the right trends. And so, and you can see it's a little high here, but it's within a factor of 2, this factor that I've been talking about. The energy sudden is completely wrong at low temperatures, and it's because it's freezing out any kind of dynamical behavior that the three-body dynamics might have. But what you are seeing at higher temperatures, above 600, the energy sudden and the coupled states are in good agreement. It is exactly in this temperature range that the star formation problem that I had used to motivate this was in need of three-body recombination rates. And this was a justification for why I said the energy sudden approximation could be reliable at those temperatures. So that plus the agreement with the classical trajectory calculations makes me think it's probably in pretty good shape. All right, so let me summarize by saying that molecules and atoms, but in particular molecules, act as coolants for star formation. Ra is an important molecule formation mechanism at low density interstellar gas, and at high density three-body recombination is very important. Kinetic feedback is generally important for recombination. It's well known that three-body terms can deplete the population of quasi-bound states. But what's important to also realize is it's also three-body collisions can populate the quasi-bound levels as well. And in general, you'll see a pressure fall off for the Ra as the quasi-bound states get populated. You don't see this pressure fall off for three-body recombination. You actually would see it if you looked at the three-body rate not multiplied by that third body concentration, but it would quickly, it's not important at such low concentrations that you don't have to worry about it. But when you go back and you look at it multiplied by the third body concentration, it's very linear. Two-body rate constants may be used to estimate the three-body rate constants at high temperatures. And this is maybe sometimes useful at the first start because the two-body processes are a lot easier to calculate than the three-body processes. So I think that I'm out of time, probably.
It's okay.
Okay, take questions.
Thank you.
Yeah.
Please.
Yeah, this is such great work. I mean, since you have this unified way of treating the resonant and non-resonant states of H2, it occurs to me that maybe instead of just saying the tunneling time is tunneling rate, I guess you say is 0 for continuum states, what about using the Wigner time delay? That would be a unified way to treat all states the same.
Well, absolutely true. Yeah, in fact, But it's interesting if I go back to this slide that has that. Yeah, so a couple things. If this tau was basically zero for a direct collision, or you could calculate it if you wanted, but in general, it's going to be so fast, right? That generally this is going to be this is going to come from the two-body activation, right? The system comes in and you get activation and you forward and backward, so you get an equilibrium constant. You don't need this term, which is three-body. You don't need this term, which is three-body. It just goes away. You don't actually. You could calculate using a time delay, but it's going to be still so fast that it's not going to matter. But in the code, it actually does exactly that because I calculate these lifetimes using a standard, Sturmian code that I wrote, and it does work for both unbound, quasi-bound, and also.
Well, there's a way to calculate the time delay with Sturmians.
Yeah, well, it's actually in the paper. You can actually calculate it, using the potential, of course, and the and then the Sturmian eigenstate together with the usual free eigenstate. Square it and multiply by 2 pi, something like that. So, but at any rate, it doesn't. It turns out you don't even need it here, right? If anytime for atomic recombination, anytime this denominator is important, the numerator is important, and so you don't even need the time delay. You only need that if you're looking in the limit of low density gas. Then you absolutely need the time delay, and that's how we calculate.
Questions? Yeah, Thierry?
Yes, about the normalization of the continuum state or the quasi-bond state. Anyway, if you want to calculate deactivation cross-section, you need to have a unitary S matrix, so you cannot normalize over the energy. You need to have L2 function to get a unitary S matrix. So the
S matrix is completely unitary as it needs to be. So I'm not sure what the criticism.
No. I mean, it will not make sense to normalize over the energy, at least to do this kind of calculation afterwards. When I know I read your paper, which is beautiful, and effectively the weight of the Sturmian removes the problem of this normalization.
The energy normalization and the quadrature weight for a Sturmian representation are inversely related. So that's why you can always work with unit normalized, basis states, whether it's bound states or unbound states. That's generally true. So that doesn't affect any unitarity issue at all.
I just wanted to know if you have now this galactic gas that collapses and forms a star. So what are probably the temperature will there will be an evolution of the temperature.
That's right.
And I was just wondering, what are the temperature windows that you are most interested in? And then you said that there's cooling. In the end, is it the hydrogen molecules that radiate off at that temperature, or?
Yeah, there's all stages of cooling. And remember, at the early universe, hydrogen is pretty much all there is: helium, hydrogen, and there's no other, maybe a little bit of lithium. But at any rate, this is the answer to your question about the temperature range. 1,000 to 10,000 is really what they were looking for. That was where most of the uncertainty in the simulations was coming from. But
and so one can see that looking at the galaxies, or that we get radiation at that temperature, or that?
I mean, there's different processes. So first of all, I should mention that the gravitational collapse simulations have more than just a couple. There's every process that is possible that involves hydrogen, and there's a whole network of things that involve hydrogen and molecules and so forth. And so all of that's in these models, and at various stages of the collapse, different things, can be dominant. And it's only once you get above, like 10 to the 8, I think, particles per cubic centimeter or something, that the three-body recombination becomes the dominant source of the uncertainty in the simulations. And that's where, and it was at these temperatures, and that's where it needed to be better understood. But there's other cooling, I mean, obviously at the initial stages when things are really hot, atoms are your primarily coolants, but those energy spacings are so large, they can only work for so long until you need molecules. And so the hydrogen molecules became the limiting step in the understanding. But then there are even other, as you get even cooler, there's a whole network of the, I guess there was this H- pathway that I think Alex may have been the first, Alex Dalgarno was the first to point this out, I believe. And so then there's other, hydrogen, networks that become important.
But also vibrational transitions are EV and EV is about 11,000 Kelvin, so that's the typical type of temperatures you need.
Right, yeah, so, I mean, the modelers are really on top of this, right? So, I mean, they pointed this out to us, right? I mean, this was very beneficial to find out what they needed. And that's why I think it's always good. That's what's so great about being at the Center for Astrophysics, of course, is that you have people who are very knowledgeable about the macroscopic simulations.
I'm curious whether you thought about this really long-range Ungerade state of H2 that has a scattering length of around 700 Bohr. If that could be of interest to look at its recombination role in the ultra-cold.
Yeah, I have to think about it. It's been a while since I've done the calculations, so I'm trying to remember exactly what the details
It's an
there were.
excited Ungerade state.
Yeah, so yeah, there's a repulsive state and then there's the attractive. We only looked at the attractive one and then used statistics to argue that that's all that was necessary. How do you think about the repulsive?
I don't know if you mean by repulsive, the 2p sigma U state potential for it.
Yeah,
Mostly repulsive, but has a very shallow well, and there are two bound states in that well.
I'd have to look at that. I don't think we
And
did.
The excited one has this huge, unbelievably large scattering length.
Yeah, no, we didn't look at that then. No, maybe I'll think about that. Do you have any reasons to think that it would be important?
Well, I mean, systems with large scattering lengths are pretty
Yeah.
interesting for FMO physics and a variety of phenomena.
Right. Yeah, I'll think about that. Thanks.
Any more questions? No, so let's thank Bob and Robert for coming.